All right. Thank you, Prash. So I hope you have a good overview about foundational models, the different aspects of it, and a bit of the history of the last few years. So my idea now is to touch upon the specific aspects here, give a little bit more in-depth information for the understanding of foundational models. And then we're going to some specific examples and a discussion. So first of all, architecture for foundational models. In theory, any model could be a foundational model, but most important is for us the specific building block, especially the transformers, because they have been fundamental in the development of foundational models. So what is a transformer? I'm not going to go into the nitty-gritties, but just for you to get a bit of a better understanding what's happening here and why it is important. So previously, especially when building language models, we had a lot of sequential models that went through the text, which made us very inefficient for parallelization. The transformer idea is we take the entire input, so for example, a large piece of text, we break it down in pieces of text and encode the individual pieces into tokens. At the same time, we are creating a positional encoding so that we are not relying on the implicit sequence of the text blocks, but we have an explicit encoding of the position of our pieces of data. And this enables self-attention, which is essentially a relationship between all of the tokens of our data that can have more or less important context for each other. And in this architecture, we see essentially the encoding of our information. Then we have the encoder block and the decoder block, which is a similar architecture where we are applying the same concepts on our target. And then we're having a cross attention that essentially relates the input and the target together because different tokens can have different significance for each other. And then we have layers to produce the output of the form we're expecting. So that's like the essential idea. From then on, transformers have different shapes. So you don't always have this encoder and decoder part. You might only have a decoder, and you might only have an encoder, depending on the focus of your model. You might also have multiple encoders for different modalities, and then you might have this kind of cross attention between the encodings of different modalities. So the important bit in here is also the self-attention that I mentioned. Again, I'm not going to go into the nitty-gritties, but to give you an idea, what's happening here is we have our tokens that are used in the three ways of query key and value. Essentially, it's just different forms of our tokens. We have linear layers to adapt them, and then they're all going into an intention head, which essentially does some kind of matrix multiplications where we are relating the tokens to each other. And then we can also mask different parts of our token relations, so we can control the importance of relations in this way. And in this overview, you can also see we have multiple of these attention blocks, so that what's happening here is we have the same architecture multiple times, so we can learn different types of relationships in our data at the same time that can be developed independently during our training. So this is the multi-head self-attention. We have multiple of these heads. And I'm going to leave it here to not waste too much time. So this is the important part of the transformers to take away really is that we are putting all of our input into the model at the same time with an encoding, rather than having to wait for sequential processing. This allowed the parallelization of a lot of the compute, which really drove forward essentially larger models with more data. So this is mostly used for language models and sequential data. For imaging data, we have vision transformers that function in a very similar concept. We're breaking down our image into patches. We're creating position encoding of these patches and put it into our transformer encoding. So here again, rather than having bits of text, we have bits of images that then we can relate to each other. So again, we have essentially in a single layer the ability to relate any kind of parts of our images to each other, which is very different from convolutional networks where we have a very limited receptive field and we need many layers to increase step by step the receptive field in the network. Convolutional networks are still relevant, so there has also been some advancements. The issue here is mostly the receptive field and that we need more complex models to get our context. So here, advancement have been focusing on building more adaptive convolutions to enable a faster increase of our context windows. Okay, so now I want to talk about data because we all know for machine learning, especially deep learning, we need big data. But what is big data? How does it look like? And how do we handle them then? This is an interactive figure if you go to the website, which essentially shows different large language models and the data sets that have been used. So we have a logarithmic scale. We can see that over time we have like more than an exponential growth in just the pure size of data sets, which really enabled some of the advancements. This was just text. For vision language models, I'm just mentioning some known examples. So over time, we have gone from ImageNet as a very important resource that was like in the scale of 1 million images in 1,000 classes that has then been extended over time. And more recently, we are in the magnitude of billions of image text pairs for vision language models. Then, of course, there is a big gap to the medical domain. In the medical domain, and I'm focusing here on radiology, so not pathology, we have also seen that like 10, 15 years ago, we were maybe in the scale of like tens and hundreds of images. That has grown significantly in some of these data sets. For volumetric imaging, for example, CT, it's still lagging a bit behind, but also these data sets keep increasing. Then our data sets also depend very much on the task we want to solve. So image segmentation is a task that is very time consuming to annotate, especially in 3D. And here we see that like just about 10 years ago, we had data sets that were literally like 10 images. And this also has increased from like very task specific, application anatomy specific small data sets to larger data sets. And now there's efforts of unifying different data sets from different groups because it's so hard to just create very large data sets due to the cost of annotation. So now that we have very large data sets, what do we do with them? How do we handle them? Because if we do like a very naive training, it really depends on having a good data set. So the paradigm of garbage in, garbage out still pretty much holds. So we have to be a bit smart and we have to understand our data set. So there's specific sampling strategies that mitigate just the assumption that we have a great data set. So I'm just touching upon them very briefly to give you an idea. So for example, if we are combining data sets from different domains or different sources, a very simple way is we can use fixed weights for sampling, so we keep them balanced and we don't oversample a data set that is just larger. We can also do a cluster-based sampling. So if we don't really know how to structure our data or we don't have more information, we can do a clustering, identify different subgroups in our data set, and then sample based on these clusters. We can also do a kind of a staged learning and staged sampling, where, for example, we structure the data set into simple tasks first, or clean data first that we have been curating. And then while the model increased in capacity, we go to harder problems to keep improving the model. There's also the concept of active sampling, where we use information during our training process, for example, the uncertainty of our predictions or the value of our loss function, to guide sampling towards data points that have been hard for the model, so we can reiterate and then in future iterations hopefully perform better. There's also the concept of augmentation-guided sampling. If we're using data augmentation, we can start with very simple augmentation, and then while the model capacity increases again, we can do harder augmentation tasks to push the model further. And the sampling strategies pretty much depend on our data. What kind of information do we have? What assumptions do we make? So it's something to keep in mind and make informed decisions. So that's the data itself. And then how are we using the data to train our model? And important question is, what do we want our foundation models to learn and how do we train them? So ideally, we want a model that is broad and transferable, so that in a simplified way, we can use any kind of input and we can solve any kind of task. Yeah. And so here I'm showing a toy example that is a bit hidden behind this panel. But the idea is we have like a 2D representation of some data points. And if we are increasing the encoding of just the data variation, we can cover more space in our encoding space, which improves the chance of having new data that fall in our distribution rather than having outliers that the model has less information about. And if we're going from left to right, the idea is that the way we encode our information is more informative for our task. So here, the colors could represent, for example, classes. So if we have a better encoding of our features for a task, then it just makes it simpler to separate in feature space. And that's a very simplistic model, but the idea is we just want to be able to handle the data as well as we can, make the information, our representation, useful as possible. But this holds for any kind of machine learning or deep learning. For foundation models, we want to use the high capacity of very big models and very big data sets. So our target here is also to learn higher level latent abstractions of our data. So this could be any kind of concepts, entities, relation in the data, potentially causal patterns, as well as part awareness and composition. So for example, the model should be able to know that a human usually consists of different body parts. So even if we only show part of a body, the model can assume like, what are the other parts? And ideally, we want to push a foundation model towards a world model. World model is the idea that we have a understanding of the entire rule set that generates our data. So this could be like the underlying physics or these concepts. So we are trying to approximate this in an ideal world. How far we get there is another question. Okay. Important aspects of training supervision. So very simple, supervised learning. We have all heard about this. So we have our data and we have some kind of reference that we use to evaluate if the model is performing well. So for this, we need annotated data. On the other hand, we can do unsupervised training where we do not have any references and we're just exploring the data set and trying to find structure in the data itself. Self-supervised learning is a way of applying changes to our input and then trying to understand or recover these kind of changes so that we are supervising the output of our model with the input. I'm going to touch upon this a bit more in detail after this. Another concept is reinforcement learning, where we have kind of a model that explains the state of the environment that our model is in. The model then predicts actions that change the state of the environment, and we then need to evaluate what is the change that we applied on this environment. Was it good or bad? And then based on this, we evaluate the action prediction of our model. Usually this is applied in an iterative way. Could be, for example, a model that learns to play a game, etc. It's probably less relevant for foundation models. There's also combinations of these approaches. For example, DIRA is trying to combine the first three strategies into a unified learning architecture. And foundational model tasks are generally self-supervised in training. And why is that? Primary motivation is being able to train at scale. If we want to make use of a massive data set, we are likely not going to get like very nicely clean annotated data. So if we don't need annotation, it enables us to just use these big data sets. Self-supervised learning, we can split it in the category of self-predictive learning. So for example, we take our data, we apply a transformation and try to recover the transformation. Or we apply noise on our data and try to recover the noise. Or we use, for sequential data, we can do an autoregressive training where based on a current data point, we are trying to predict the next data point. Or one approach that has proved very effective is mask training, where we take parts of our data, be it in space or in time, that we mask out, and then we are training the model to predict the missing pieces. On the other hand, contrastive learning is a concept where we take two different inputs, put it into our model, and then typically we look at the latent representation of our data points, and we want to evaluate how close are they in the latent representation. And then, for example, we want to be able to have different data of the same thing to be close in latent space, and different concepts to be further apart. A more specific example for this is, for example, we're taking a CT image of the lung, and we have different views or different crops or different patients, and they should be close together in latent space because it's still an image of a lung. On the other hand, if we have a lung and a brain, they should be further apart because they're very different anatomies. Yes?
I'm trying to figure out how that requires you to define the sets, right? So
yes. So you need some kind of information. So you might have some meta information. So for example, you probably know when you have your data if it's a lung scan or a brain scan. So in a way, you have some additional information, but usually they are very basic.
You're trusting the metadata.
Yes, likely. Or you can also, so for example, if you use data augmentation, you can even avoid this by just taking augmented views of the same data sample, and then these should be close together. And if you take random data samples, they should be further away. Okay, the training that we choose to do impacts a bit of the architecture. So just as a brief note, usually the encoding is the most important part of our foundation model because we want this rich representation of our data. But then depending on our task, we also need like some task-specific heads. So if we do something autoregressive, denoising, we need the decoder part to be able to compare input and output. If we do this kind of contrastive learning, we need to be able to classify our data. Or other concepts might even use complete auxiliary networks. So for example, for a student-teacher kind of setup, we have potentially multiple networks that interact. And once our model is trained, oftentimes we're dropping parts of this network that are then not needed further. So potentially we end up with a foundation model that is just the encoder because that's what we want, and we expect people to add on this whatever they need for their task. So it really depends what is the application.
So the self-supervised, the pre-training is basically to try and get each component of the network to have a good latent representation of the distribution of the data.
Yes. So for foundational models, the idea is we have loads and loads of data and we have a massive model. So we're trying to just understand the data and the higher abstract concepts, and this will all be in the encoder part. So that's the very important bit. And then the task head can be much more light in the size of parameters, and thus also tends to be easier to learn.
And so the generalization bit is that you just have this huge model that has a better, because I mean, for foundation models, when they're trying to learn a decent latent representation of data, right? But this is a more powerful latent representation of all the variability of the
Yes.
data that then can be used for more slightly more generalized tasks.
Yes. And because the models get so big, they have just more capabilities that weren't really possible before. So we're just seeing like emergent properties that you wouldn't see on models with smaller parameter sizes. All right. So here's just like a brief overview about the scale of training. So here we just see the compute essentially that goes into training of models. And again, over time, we see more than an exponential growth. This also is connected with the AI bubble and companies having a lot of money to invest into compute to train more and more intensive on very big pieces of hardware. Okay, so now we have our model, we have it trained. Then the postulation of foundational models is we can use it for a lot of different tasks, right? So how do we actually do this and use it for different kind of tasks? So it's a bit the adoption to different tasks, and I'm also going to touch upon bias and scope. So some models might be able to be used in a zero-shot or few-shot fashion, where you just input your data for a task and you get your output out of the box. For few-shot, you usually provide some kind of samples. So when you have language models, you might just explain how to structure your data, or you might provide some images as an example, like, okay, now look at this. This is what I want to classify. Please do it. So there's some examples, especially all the kind of language models. Then we might also want to fine-tune our foundation model for a specific task we want to do, or for specific data domains. For this, we update parts of the foundation model. Usually, we don't want to update the entire model because it's so big, but we might pick specific parts, or maybe just the task head to update it with our data. Some of the foundation models themselves have been fine-tuned. So, for example, BERT is initially self-supervised and then fine-tuned on a handful of different tasks. Distillation is another adaptive mechanism where oftentimes we want to condense the model into a smaller parameter size to be able to make it more usable, or to extract specific kind of task knowledge. An example with Dino v3 that has been provided in loads of different parameter sizes. Model bias. Yeah, biases are, in a way, any assumptions that go into building our model. So, for example, there's preferential bias. That is, for example, how we choose our loss function. What kind of regularization do we need? So that's like a very old concept from classic machine learning strategies, where essentially the way how we apply our assumptions form what kind of models we're building. I'm not going into detail, but just as you know, like if we are regularizing our data, oftentimes it means we have few data and we want to be able to generalize, so we can't overtrain on our few data. We need some kind of smoothing out to be more general. Yeah, there we are. Then, especially for deep learning, we see a lot of architectural bias. So we have probably mentioned all of these bits, but just quick again, self-attention enables these long distance relation between our information. CNNs very local connectivity that can be strong for a specific application, but has its limitations. Recurrent models have the sequential pattern. So the choice of our architecture really determines the behavior of our model. Then there's also something like implicit bias based on the optimization we use. So different optimization algorithms will go through our loss space differently, so they will converge to different kind of solutions. Also, our data is very important, as we mentioned before, but also what kind of assumptions we apply on our data. So if we're using augmentation, we assume that certain changes on our data don't change, for example, our class label. These are all assumptions that go into the model and how it will behave. So, as I said, bias influences how our model behaves. And here, a concept that has been mentioned more recently in papers is the kind of task model alignment. So we need to keep in mind that the way we build our model has to be in line with our task, and we see transfer capabilities of varying quality depending on what our model and what our task is. So certain things just don't match well together. And overall, you could say that in traditional machine learning, bias helps avoid overfitting, whereas now, when dealing with giant foundational models, assumption on our bias shape the way we learn our representations and how we impact the transferability. Right. So now that we have our model, we have it trained. Very important question is, what is the scope of our model? And this is usually limited based on the one hand, like our data domain, on the other hand, the task we can do. So it goes from very narrow to very broad. And essentially, like we have all kind of different models and sizes and what they can do. And the question is like, where do we draw the line? What is a foundational model? What is not a foundational model? And that's probably one of the big questions that keeps coming up. Because if in doubt, just call your model a foundational model, and you might get a few more hits when people search your paper. But then, opinions might vary. Yes, but then again, whatever definition you look up for foundational models, they're usually very vague. So I think rather than just saying this is a foundational model, we probably need to discuss why is it a foundational model? What are actually the capabilities? What went in there? Okay, so I hope you got a little bit more understanding of all the bits and pieces that come together. So now try to be awake. We're getting to the interactive part. Yeah, so
that's too much expectation.
But
just so that you don't fall asleep, that's kind of it.
Right, we're still all here. So big question, is it a foundational model? So turn around your exam papers. ChatGPT, is it a foundational model? Okay, we have a couple against, majority for. So common arguments that are being made is, well, it's trained on a massive scale, broad transfer, all of these things, emerging capabilities. But then on the other hand, ChatGPT is an application. It's not really a foundational model. ChatGPT uses models like GPT-5 or whatsoever. And really, like, when you want to be pedantic, I guess you really need to draw the line and make a difference between what is an application, what is a software tool, and what is the foundational model that might be underlying.
I mean, it's a bit more striking with Claude. Claude is just a product, and it's not the name of a model. You know that if people are using Claude, then they will have Opus 4.5 and all of the ones that are listed.
Sure, GPT too. You can.
Yeah, but it's still the same name. So it's just they're just making the difference between what has been trained and then how it's being used. So just the differentiation with the product. And yes, it's better. We shall.
All right. Next one, Sam, segment anything. We see opinions for and against. So arguments is, okay, we have the transferability, we have zero-shot capabilities. On the other hand, some people might argue it's a narrow task, so it only does segmentation. Is it a foundational model that only does one thing? Yeah, possibly limited on the modality. But then in the end, we would say it is a foundational model. And when you talk about scope and breadth, this might very much depend. So everything is relative to a degree. And depending on your domain, you might be limited in how general you can be possibly. So then we've mentioned Dino before. Do we have opinions, people? Do you think Dino foundation model? Yes, no. So again, yes, we have arguments for and against. So some people might say, well, Dino, you can't really prompt, it's not interactive. But then this is not really an argument against the foundational model, because as we saw, like essentially a potent latent space can be a foundational model if you just need to plug in a small task head. Then NNUnet. Most people should have heard about NNUnet. Is NNUnet a foundation model? Well, that's an interesting discussion. So yes, essentially, NNUnet is a training regime. NNUnet builds UNet models, and there's like a lot of bits and pieces that come together. So again, it's like, it is something that generalizes very well. So it kind of looks a bit like a foundational model, but it is a different beast.
The overarching concept.
Exactly. So it's mostly the concept of having a training regime that adapts to your data and then creates a specific model that performs pretty well. And